All right, so let's get this one going now. Operations radical expressions. You will simplify radical expressions. That's our whole goal here. Now, this is a kind of a beginning thing, but it should be a review of stuff that you've done before. So we're going to kind of continue this from, say, something else that you should remember. You did it like hopefully in Algebra 1, and you hopefully did it even in geometry. And then we'll kind of go from there. So, first thing. So let's talk about radicals. Okay, what is a radical? That's that square root symbol that you're so used to. So like you know that the square root of 4 is equal to 2, the square root of 9 is equal to 3, the square root, and I'm going to stop it right there, the square root of 25 is equal to 5. However you may remember that explanation of why it's the square root of 4 is 2 and stuff like that, kind of go from there. I always think about it is that the square root is got a root of 2. We'll talk about that in a little bit. And I'm looking for things that would, what number times itself would give me 4? What number times itself would give me 9? At the same token, how about if I start looking at the cube root of 8? Notice here now I'm saying this, which is called an index, is equal to 3. So now I'm looking at what number times itself 3 times would give me 8. And that would be 2. What cube root of 27 would be 3. The cube root of 625 would be 5. Oh, I'm sorry, not the cube root, 2. Got to make sure I read that. The fourth root of 625 would be 5. So, like on the 27, it's because 3 times 3 times 3 equals 27. On the 625, it's because 5 times 5 times 5 times 5 equals 625. So, we'll discuss different methods of how you might work that out, and I'll make my recommendations and kind of go from there. So, let's start off with just square roots, which is that's what you should have been looking at previous times. I'm just going to give you this table. You might want to copy it down. These are all the perfect squares up until 18. Now, if you could do this all the way to 25, that would be great, because I would prefer it up to 25. Like I can tell you the square root of 361 is 19. The square root of 400 is 20. The square root of 441 is 21. The square root of 484 is 22. The square root of 529 is 23. The square root of 576 is 24. And the square root of 625 is 25. Whatever. Okay, but this table would help you, because what happens here is there's actually 2 ways that I know of to say find square roots or to simplify. Okay, there's the perfect square method, and then there's the factor tree method. Now this is for those that don't come out nice and even like this. Okay, so kind of keep that in mind. Okay, I'm going to fast forward that. Okay, so let's look at the square root of 32. From the perfect square method, what you would do is you would find the highest perfect square that divides into 32. So if you look, 32, after 32, there's a 25 and then there's a 16. Okay, so you've got 25 won't go into 32, but 16 does. 16 goes into it 2 times. So 32 divided by 16 gives me an answer of 2. So now I know 32 can break up or divide up into 16 and 2. Now, what's the square root of 16? The square root of 16 is 4, and that would be there. And the square root of 2 has no perfect square, so that's it. That's your answer. So the square root of 32 simplified is 4 square roots of 2. That's how you say it. It's 4 square roots of 2. Notice that the one that had an even square root went to the outside, and then whatever was left over stayed inside. Now, the factor tree, you want to look for pairs. So like I say, what goes into 32? Well, 2 and 32. Or maybe you say 8 and 4. It really doesn't matter what numbers you think of as long as you know numbers that can go into. 2 goes into 32 16 times. 16 goes into, or 2 goes into 16 8 times. 2 goes into 8 4 times. 2 goes into 4 2 times. Okay, now when you look at a factor tree, you look at the end numbers there, and you're looking for pairs. So I'm looking at this right here, and I'm going, okay, I got a pair of 2's and another pair of 2's. So you write the pairs on the outside. This pair is represented with that number. So what you're writing on the outside is what those numbers, what those pairs were. So it was a pair of 2's, another pair of 2's, and then the leftover 2 goes inside. This leftover one goes inside. So what's 2 times 2? 4. So it's 4 square root of 2. So you can kind of see, no matter what, you're going to kind of get to the same answer. Okay, so let's look at 84, and I'll do it by both methods. Okay, so 84, let's see here. 64, no. 49, no. 36. What I'm doing is I'm like looking at all the perfect squares on my table that divide into, to see if any of them will divide into 84. Now, it doesn't happen until you get to 4. I mean, you literally work all your way down. I mean, it's 49, 36, 25, 16, 9, and then finally 4 divides into 84 21 times. So what's the square root of 4? Square root of 4 is 2. There is no perfect square for 21, so that's your answer. 2 squared to 21. With the factor tree, you can say 2 and 42, 2 and 21, 3 and 7. Notice, and when you're doing by the factor tree, you're looking for numbers that divide. If it's an even number, you can divide by 2. If it's an odd number, maybe you look to see if it can divide by 3, by 7, by 11. If it ends in a 5, you know it's divisible by 5. You know, so know your division rules. So which one of those would be easier for you? I don't know. I used the factor tree a lot more before, but now I like to use the perfect square method. Anyways, I got a pair of 2's that go on the outside, and I got a 3 and 7 left over on the inside, and 3 times 7 is 21. So there's my 2 answers. So you can kind of see how that works. Now, when you have, of course, this is Algebra 2, and we got to make this a little bit harder. So let's talk about when we have a variable. First off, let's talk about the fact that what these are called. Don't forget that this little square root symbol is actually called a radical sign, or just a radical. The number that's inside is called the radicand, and the n, the little number that may be on the outside, if there's no number, that's presumed at 2. So that's one of the few times that when you don't have a number, you presume something other than 1. That's called the index. Okay, so what we do here. Okay, so we already know. Okay, dang nabbit. Hate it when I do that. Okay, we already know there's no number there, so I'm going to presume that's a 2. And then, okay, so we already know 32 is 16 times 2, which we said was 4 square roots of 2. Okay? Now, so the 4 is going to go on the outside. Now, the variable for the x is also going to go outside before the radical symbol. We like to have them be in front of the radical. So we like to have the radical on the end. Take the 8, the exponent, and divide by the index. So 8 divided by 2 is 4, and it comes out nice and even. So there are no leftovers, and you say 4 times x to the 4th, and then you have in the radical a leftover 2, and that would be your answer. So 4x to the 4th square root of 2. Now, the other way I would sometimes normally do this was I would actually write out how many x's there were and then circle the number of groups, because this represents how many groups there were. And there was 4 groups of those x's. Okay? So there's a couple of different ways you can look at this, and if you do have questions, I'm more than willing to answer more about this. Okay, so let's look at this one. 98 x to the 6th, y to the 5th. Okay, 98 is 49 and 2. I mean, if you look at 98, under 98, there's 81. That's not going to divide. There's 64. That's not going to divide. You get to 49. That does divide. So again, you're using those perfect squares. The square root of 49 is 7. And then I'm going to have x and y. Okay, 6 divided by 2 is x cubed. 5 divided by 2 gives me 2, but there's a remainder. So what's the remainder? Well, okay, that remainder is 1. So that means there's going to be a y that's still left in. So the 2 and a y will stay in. Okay? And if you want to draw it out, there's 5 y's right there. And notice I have 2 groups, but with 1 y left over. And that 1 y that's left over is what goes under the radical symbol. Okay, so now let's look at nth roots. Okay, what does that mean? That means something bigger than a square root, to be honest. So let's look at the first example here. Cube root of 375. We say that third root of 375 are cube. In other words, what number times itself 3 times would give me that? Well, nothing comes out even. So then we go to, like, say a factor tree. So if I do the factor tree, 5 and 75, 5 and 15, and 5 and 3, well, now, because of the third root, I'm now, instead of looking for pairs, I'm looking for something that occurs 3 times. You can see here, the 5 occurs 3 times, so I would write a 5 on the outside with a 3 left over. And notice again, I still put the third root there on the radical. Okay, so here's another example. 240, well that's 10 and 24. 2 and 5, 24 is 3 and 8, which is 4 and 2, and then 2 and 2. So if I look at those end branches, which my little tree there is a little funky, so maybe I write the numbers all down in a nice little single line so I can see them a little bit better. I can see I've got one group of 2's that occur 3 times, but I still have a fourth 2 that's still left over, a 3 and a 5. That fourth 2 times the 3 times the 5 will give me 30, and that stays inside the radical. So there you can go with that. Now, is there other ways I could look at that? Well, yeah, you could say, oh, I'll come back to this in a second. You could say work off a table. Like here's a cube table. Maybe you pause this and copy this down. Here's to the 4th power. So here's a table to the 4th power. Notice how high these numbers are going. And then maybe you make one to the 5th and 6th. But with the 5th and 6th, honestly, I'm not going to go that high. So like if it's the 5th power, it's like 2 to the 5th power, 3 to the 5th power, 4 to the 5th power. That's about it. Or 6 to the 5th power, 2 to the 6th power, 3 to the 6th power, like that. It's not like I can go that high because those numbers get pretty big. Anyways, how would I use that? Well, if you take this example right here, you could have easily have said, if you had your cube root table, okay, what cubes can go into this? And look at the cube root table, the first one under 240 is 125. That doesn't divide into, 240 divided by 125 doesn't divide evenly. The next one is 64. Again, doesn't divide evenly. The next one is 27. Doesn't divide evenly. But 8 does. 8 and this would be 30. Well, and the cube root of 8 is 2, and then you would still be left with the 30. So that's, if you have this table, that can make things maybe a little bit easier for you. At least I think so, because this is almost like multiple choice. These are the numbers you can use. And the factor tree might take a little bit longer. Okay? So now let's look at the next part. Let's look at another one. 54, x to the 7th, y to the 9th. Okay? Well, 54 is 27 and 2, and I'm just going to stop there. 27 times 2, or the cube root of 27 is 3. So that means I'm going to have a 3 on the outside. I mean, the factor tree gets continued, but you can see a 3 on the outside with a 2 left on the inside. and then what do I do with the x? Well, 7 divided by 3 is 2 with a remainder of 1. 9 divided by 3 is 3 and no remainder. So that would mean there's no y's inside the radical, but there was for the x. And I'm going to rewrite it so I can make it look a little nicer. Okay? So you can kind of see there like that. How about the 4th root of 2,592, x to the 11th, y to the 7th? Well, under 2,592, you've got a 4, and if you look at the 4th root table, you've got 1296. 1296 goes into that 2 times. So there you go with that. So that's, and this 4th root of 1296 is 6. So you know because of that, that 6 goes on the outside, with a 2 still under the radical. 11 divided by 4 is 2, x squared, but has a remainder of 3. Because remember, you're trying to get things in groups of 4. 7 divided by 4 is 1, with a remainder of 3. And again, y'all should be able to figure that out as far as dividing and remainders. But if you have problems with that, you know, again, ask questions and I'll try to discuss it. So there's those, and you can kind of see how that works. And here's some more examples. This is going to be my last set of examples, and then we'll kind of go from there. So what happens when I have the negative 4th root of 16, g to the 16th, a to the 24th? Well, negative is just going to be a negative. The 4th root of 16 is 2. The 16 divided by 4 is 4, and 24 divided by 4 is 6, and that's it. There's nothing left over, so that's your answer. How about 243, a to the 20th, b to the 26? Well, the 5th root of 243, notice that's a 5th root, is 3. 20 divided by 5 is 4, so that's a4. 26 divided by 5 is 5, but with a leftover 1. So there's 1b that would still be under the radical symbol. Now here's a funky one. 6th root of 3x y cubed raised to the 12th power. Well, When it's raised to that, like, you see how that's in parentheses? That means then ignore what's in the parentheses and just look at that exponent of 12. What's 12 divided by 6? 2. So that means I take everything that's in that parentheses and just say it's the 6th root of that is that squared, for lack of a better way of being able to put it. Anyways, this is getting kind of lengthy, and this is pretty much it, but there you go. And we'll have questions. Please, if you do have questions, make sure to ask, and I will do my best to help answer them for you. All right? Thank you very much for your time, and I will see you when I see you. Take care.